All right, class, welcome to section 5.3, radical functions. So again, if you do remember from our library of functions I gave you back in section 1.3, the two radical functions that we discussed were the square root and the cube root function. So let me remind you of what those graphs looked like. And I'm just going to not make it quite as pretty. I should have put myself a nice little grid. But the square root of x, again, if you remember the domain of the square root function, you only can have numbers inside the square root that are greater than or equal to 0. So in other words, you cannot put negative numbers inside. You can if you are thinking of complex numbers or imaginary numbers, but as I explained to you, anytime we're talking about functions, this represents the real number line. This represents a real number line. So we cannot place imaginary answers on the xy plane. Yes. Again, when we talk about the domain of a function, you can even look back at the definition of the domain. Back in 1.2, it said that it's the possible x value, the x value that we can plug in order to produce real numbers. Okay, so we cannot produce imaginary numbers. Okay, so again, if I plug in the square root of 0, 0, the square root of 1 is 1, the square root of 4 is 2. So very well, if you think about it, the square root function is half of a parabola sideways, not the full parabola. Again, the graph of a function has to pass the vertical line test, so we couldn't invert the whole parabola. For every x value, we can only get one possible y value, so therefore, the graph of a square root function is just half of a parabola. Now, for the cube root function, here, the domain of the cube root is all real numbers. You can have very well negative numbers inside a cube root. Because again, when cubing a negative, you get a negative. When cubing a positive, you get a positive. For squaring, everything turns positive, yes? So the graph of the cube root function almost looks like the square root function, just two of them. So again, the cube root of 0 is 0. The cube root of 1 is 1, but now the cube root of 8 is 2. So it's a little bit more stretchy. And here I can even show you guys. I have a whole bunch for them written, but here. Let's look at the graph of simply the square root function. So what does square root of x look like versus the cube root of x? So if you remember, I showed you this in the first chapter. Under math, you find the cube root button on your graphing calculators. So let's graph the square root function and the cube root function. It does it both. So the cube root almost looks like the square root. So there you go. This is, can I do it in different colors? Let me just do this really quick. Yeah. Okay. Let's see if I can do that. And here's the graph. Yes. So the square root function is the green one. As you see, it only exists on the positive side of the x-axis. Keeps on going and on going. However, the cube root function is way closer to the axis because it's way narrower, right? Remember, the cube root of the square root of 4 is 2, but the cube root of 8 is 2. So here it is. I keep playing with this. The point is, yes, the cube root function goes all the way left and right, negative infinity to positive infinity, but the square root function only exists on the positive side of the x-axis. Okay, so there it is. All right. And of course, we're going to use our graphing calculators quite a bit to positive side only, both sides. Way narrower, way closer to the x-axis, actually. All right, so here it is. Remember that any square root function will have restrictions on the domain, but the cube root functions will have all real numbers as the domain. So I already discussed that. Now, let's graph these functions using transformations as you saw with the absolute value function, with the quadratic functions, graphing with transformations is way, way better. So here I'm going to graph first the regular square root function, which again goes through 0, 0, 1, 1, 4, 2. So in other words, square root of 1 is 1, square root of 4 is 2. Here's my half a parabola. Then let's go to green. What is the next transformation? The square root of x minus 1 means that the graph is just simply going to move 1 unit to the right. And then let's do it in green. This last transformation is the square root of x minus 1 and then plus 4. So this graph from here is going to move 4 units up. So 1, 2, 3, 4. 1 up. 1, 2, 3, 4. So all the way up here. That's it. And this is the answer. Okay. Now, if we wanted to solve this problem and graph this function by finding intercepts, you already see from the graph we obtained that there are actually no x or y-axis intercepts. This graph, the red one I highlighted for you, doesn't even at all cross any axes. And you can see, let's find intercepts. In other words, let's make x0 find y. So plug in a 0 for x. What do we get? Well, we're going to get the square root of 0 minus 1, which is negative 1, plus 4. That's an imaginary answer. So it does not produce a real number. We cannot plug in 0. It's not in the domain. As a matter of fact, what's the domain of this function? Well, we have to make sure that the quantity inside the square root, we talked about this in chapter 1, those were the square root and the rational functions were the ones that we kept worrying about. So we said, okay, you need to make sure that the quantity inside the square root is greater than or equal to 0. Well, what that means for our x's is that x itself has to be greater than or equal to 1. So in other words, the only values that I'm allowed to plug in to these functions are numbers greater than or equal to 1. So I couldn't even plug in 0, right? Now, if I set the function equal to 0 to say, okay, now let's make y equal to 0. Let's say see what we get for x. We end up having to solve this radical equation. Oops, plus 4 equals to 0. Yes, so we're setting the function equal to 0. So instead of f of x, I'm going to write a 0 and then solve this equation. Great. What happens? Well, the first thing we learned back in section 5.1 is that we need to isolate the radical, right? So subtract the 4 on the other side. Well, a square root, a positive square root cannot equal to a negative, as we encountered in that section. I said, don't even bother going further because whatever you get for an answer will not be when we check the equation, it's just not going to be an answer because we get what we call an extraneous solution. So that's not going to work. So again, with just these points, we're not even going to come up with any intercepts. There are none, as you see from the graph, right? Now, one other way, of course, if those points don't work, you can plug in a whole bunch of others, so you can still try and graph by finding intercepts or other points, if those cannot be found. So remember, what kind of values are we even allowed to plug in? More than one. So fine, plug in 1, plug in 2. Plug in 3, 4, see what you get, and then you can slowly come up with some of these points and graph the function. But as I showed you in the past, transformations are the best. Okay. So let's remember, and we've been practicing on transformations section after section. So I'm going to do that. Start with a square root function. Okay. Again, I'm holding on to a few good points like I did with the quadratic as well for you in the last chapter, in chapter 3, the absolute value. So here it is. Now, the next transformation I want to worry about is the x transformation. So I have the square root of 2 times x. Now, if you remember what that does, whenever there's an x transformation, we do the exact opposite. So instead of multiplying all the x values by 2, we divide all x coordinates by 2. So we always do the opposite. Now this x coordinate is a 0, so it stays a 0. This x coordinate here is a 1, so it goes to a half. This x coordinate is a 4, so it goes to a 2. So what we do, or what's happening, is that the graph gets compressed horizontally by a factor of 2. So it gets squished in towards the x-axis. And then finally, the last one is a y transformation. So we take this square root of 2x function and minusing 3. So we're moving this graph 3 units down. This half goes here. 3 units down it goes here. So it's squished in towards the x-axis. We should be able to find an x-axis intercept and definitely a y-axis intercept. It's right here. So let's see. This is our graph. This is our answer. And of course, here it is. I'm going to take these out. And here is our function. I'm going to graph it for you. So it's squished in. You don't quite see it because here it is. It goes all the way to -3. And then on a graphing calculator, you should be able to see this better. And bring it more to the kind of numbers that we're dealing with. So the graph starts down at -3 on the y-axis, and then it's a little bit squished in closer to the y-axis, and it just keeps on going. So let's see, how would we have found intercept? So again, make x equal to 0, find the y. So if I plug in a 0 into this function, I'm going to get the square root of 2 times 0 minus 3. And 2 times 0 is 0. And the square root of 0 is 0. And 0 minus 3 is -3. So definitely we have the point of coordinate 0, -3 on the graph, as we already see. Right? Now make y equal to 0 and then solve for x. So again, it goes back to what we've learned to solve in the in section 5.1. Okay. So square both sides to get rid of the square root. So that's going to be a 9. And the square root's gone. Divide both sides by 2. So x is going to be 9/2 or 4.5. So indeed, I made this go a little too low. The graph does cross at 4.5. So yeah, don't bend it too much. And this is actually better. It mimics the graph above better. Okay. So here are my points. Again, it's one or the other, yes? So I have 4.5 and 0. Now, with just 2 points is not going to be enough. So just because it crosses through these 2 points, it doesn't mean it has to start here. So you have to be really careful about this. However, you do have your graphing calculators to help you and stop you where you need to be stopped. Okay. Again, with the transformations, we get the bigger picture. So here it is. Start with the square root function, 0, 0, 1, 1. 4, 2. Hold on to a few points because that's how we graph using transformations. We just hold on to different points. The next operation is to multiply the function by a negative 1/2. So take all the y values you had before, the y coordinates, by negative 1/2. So of course, the 1/2 makes the graph compress vertically by a factor of 1/2. So the graph is going to go halfway in towards the x-axis. However, it's also multiplied by a negative, so that's going to make the graph flip over the x-axis. So we'll do both. Now this y is a 0 times negative 1/2 is still a 0. The y coordinate here is a 1 times negative 1/2 is negative 1/2. This y coordinate is a 2, and 2 times, excuse me, negative 1/2 is negative 1. So there you go. It just got flipped about the x-axis because all the y's are now negative, but also got compressed vertically by a factor of 1/2. So it came closer towards the x-axis. Finally, the last transformation or function is take the negative 1/2 times square root of x and add 3 to it. So clearly all these points are going to go 3 units up. So here it is. Don't make it too shallow. Still moving. So again, don't make it horizontal like I did with the last problem. It's too much. Okay. So again, you can solve finding intercepts, plug in 0 into the function. Negative 1/2 times the square root of 0 plus 3 is going to equal to 3. So as you see, we have the point of coordinates 0, 3 on the graph. This one's pretty neat. If I set the function equal to 0, let's see what we get. Again, it's just reviewing solving radical equations. So I'm going to minus the 3 over. Divide by negative 1/2. And if you put this in your calculator, you're going to get a positive 6, because again, to divide by a fraction means to multiply by its reciprocal, but you can very well test it with your calculator, no problem. And then you square both sides, so x is going to be 36. So in other words, this is going to go very slowly but surely, and eventually at x equals to 36 is where I'm going to reach the x-axis finally. So definitely not on this graph. All right, now let's not even worry about intercepts. It's really a waste of time, I think, but fine. We can try it. Best way to graph these functions is still, I think, by using transformations. So let me start you with the cube root function. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of negative 1 is negative 1. And then about at 8, the cube root of 8 is 2. So it's very, very shallow. This is the cube root function. And then, of course, you know that we're going to move it by now. You could even do both transformations at once. So we're going to move this graph 1 unit left and 2 units down. So each of these points are going to move in left 1 unit. And then finally 2 units down. These graphs are very shallow, so they don't bend much, very horizontal. Oops, move it down 2 units. So take this graph and move it down 2 units. And there it is. Okay. Now, if we wanted to find intercepts again, let's see, if I plug in 0 for x, the cube root of 0 plus 1, which is, by the way, 1, minus 2. Cube root of 1 is 1. 1 minus 2 is negative 1. So I should see the point 0, negative 1 on the graph, and here it is. If you set the function equal to 0 and solve for x, okay. So again, we're going to add the 2 over to the other side. Then to get rid of a cube root, we will cube both sides. That takes away the cube root, and 2 cubed is 8. So minusing the 1 gives me an x of 7. I made it cross a little too soon, so it actually crosses here at 7. So it's very bendy. But just with these points alone, you wouldn't be able to graph the function. You need this turning point, right? This one key point in the cubic function, right? Where does it switch? So only transformations really will do that for you. Okay, so let's just graph using transformations only. Best way. But if you do want to find points, you would need more than just those intercepts. So here's our cubic function. Not cubic, but cube root. And it is a cubic function sideways, by the way. So if you look at it, it looks like the cubic function sideways. This time over the whole domain, there's no restrictions to cube roots or to cubes, right? The domain and range are all real numbers. Okay, what will be the next transformation? It says to move this graph 3 units to the right, right? So x minus 3 means shift the graph 3 units right. Okay. And finally, times 2 means stretch the graph vertically by a factor of 2. So times 2. So this guy, y value is a 0, so stays a 0. This y value is a 1, so it's going to move to 2. This one's going to move to negative 2. So the graph is going to be way wider. There you go. And that's ultimately where the graph ends up being. Again, you can solve and find a couple points, but the 2 intercepts alone that you will find would not really give you a good clue on where the turning point in this graph is. So it's not helpful at all. But of course, in contribution with the graphing calculator, you should still be able to draw a nice comprehensive graph. So here, let's just do one more. Don't know what I have here. Let's see, what did I have? Minus 3. Let me delete this. And then put in a times 2. It could be in the front, but I didn't have room. So I have a 2 times the, yeah. So see how the graph is just goes up higher. It does cross as we have it at actually 3. So if you zoom in, you see the graph crossing at 3. And the other one is about a negative 2.7-ish. Definitely whatever we would get if we plug in a 0 into our function. But it's not as narrow as the other graphs. It goes up twice as fast. Okay. So again, this point right here, you would get, if you plug in 0 into the function, what is 2 times the cube root of negative 3, right? Because 0 minus 3 is negative 3. And you can very well have a cube root of a negative number. So negative 2.88, right? So if you remember on the graph, we were quite close to negative 3 with that y-axis intercept. All right, so that's it. Now let's just try and guess what the equations of these few graphs are. If you look at them, these two functions here are definitely square root functions. And then on the one on the right is definitely a cube root function. Okay, and you can write y or you can write f of x. That's totally fine. So let's see. This graph here, what happened to it? It got moved 3 units to the right. So I have an x minus 3 inside the square root, right? The graph moved 3 units to the right. And then it simply got flipped about the x-axis. So that must be its graph. The cube root function here moved from where? 0, 0, 3 units up. And 1 unit left. So therefore an x plus 1 inside the cube root. And then plus 3, it went up. So again, remember, with the x transformation is always the opposite of what you see. And then with the y transformation is exactly the same. This one here is a square root. And if you look at it, whoops, where did it go? If you look at it, it's a little more stretchier. So a normal square root function, it goes 1 point in and out, right? So it's like a square root. Where did the graph go here? So the square root function immediately goes 1 to the right, 1 up, right? Kind of exactly like our quadratic function. And if that point is different, that means we must have stretched it somehow. So I want to kind of see what's happening here. It almost looks like it's stretched almost 2 ways, but it's not quite the same. So let's try that. I have a square root for sure of x plus 3 because we moved 3 units to the left. Yes. But we are not sure how stretchy, right? It definitely got stretched vertically by a factor. So let's put that a value that we have with all our polynomial and even the quadratic function. So we're going to use this point of coordinates. I definitely see it passes through 0, 3. Yes. So let's use that point to find this a value. So plug in a 3 for y. Plug in a 0 for x, and then let's see what the actual a value is going to have to be to give us that specific intercept. So divide by 3 by the square root of 3. You can give me a decimal, but if you remember from your other algebra classes, 3 divided by the square root of 3 is just the square root of 3. So that's the value right here. So you can even think, this was a tricky one, you can definitely multiply square root functions together. So I multiply both these quantities inside the square root, or you can write it as a 3 times x plus 3 in a parentheses. So it's kind of like maybe this graph got compressed horizontally by a factor of 3. Now, if you didn't really see that and you thought, oh, it's like 2 times higher, and you put a 2 for a, I wouldn't mind. But yeah, square root of 3 is 1.7-ish. So it's not quite a 2, it's a 1.7-ish right there if you see it. So what gave it away for me is that I see exactly it crosses through a y-intercept of 0, 3. So I went that way. Okay. All right. This is it. Just graph using transformation and using your 2 parent functions, right? Toolkit functions, we call them, or basic functions, using transformations.